Students, in this video, we're going to go ahead and go over groups and families of the periodic table. So remember from the last video that groups and families are the columns on the periodic table. And so there's a few special names for some of these groups and families. So we're going to go ahead and go over these. We're going to start with the alkali metals, and the alkali metals are going to be in group 1 of the periodic table. So right here, now notice I did not shade in hydrogen because hydrogen, even though it's in group 1, it's not a metal, it's a non-metal. So it is not considered an alkali metal. So remember from the last video that all of these in here have one valence electron. And that means that they're all going to form a +1 charge because they're metals, so they're going to lose their valence electrons. And they all have the same ending electron configuration of S1. Okay, this first number in front will change depending on the energy level, but the rest of it will stay the same. Now, these particular metals are very soft, so you can actually cut them with a knife, and they are explosive in water. So if you watch one of these videos down here at the bottom of the screen, you can go to the PowerPoint and click on those videos, and it'll show you how they react in water. They also combine with the halogens, which are over here in group 17, in order to make salts. Salts, we think about, our table salt, NaCl, but really a salt is any ionic compound. Okay. So then next we have the alkaline earth metals. Let me clear my drawings here. My alkaline earth metals are going to be in group 2. Oopsie. So these ones right here, those are my alkaline earth metals. So all of these ones, remember, are going to have 2 valence electrons. And then they have a +2 charge because they're going to lose those 2 valence electrons, and they end their electron configuration in S2. Now these guys are not as reactive as the alkali metals. The alkali metals, this group here, those are the most reactive metals because they have the least valence electrons. Those electrons are going to be very easy to be lost. And we're going to talk about why that's the trend when we get to periodic trends next week. But these ones are the most highly reactive, the alkali metals, this group here, most reactive. These ones aren't as reactive because they have a little bit more valence electrons to lose. They have a little bit more attraction with the nucleus. These guys are not as soft as your alkali metals. They have a very high melting point. And you're not going to find them pure in nature. So what that means is you typically aren't going to find like a chunk of magnesium walking down the street or a hunk of calcium. Okay, typically in nature, they're going to be found bond to something else. A lot of times they're going to form a compound with oxygen called an oxide. All right, let's take a look at the next one here. The intertransition metals, these ones are going to be your F blocks. Okay, now these are called lanthanides and actinides because of the first element right here. But you guys, those are written on the periodic table, so it's nothing that you have to memorize. A lot of these are man-made, the ones after uranium. Not all of them are man-made. A lot of these are radioactive because we're getting into those bigger elements. The nuclei start to become unstable and they start to decay a lot quicker. Okay, you do not have to know valence electrons for these ones. They behave a little bit differently because they're not representative elements. And you don't have to know any charges. We don't usually use these ones when we talk about ions, so nothing to worry about there. Okay. Then we're going to go into the transition metals. That's our D block. Okay, everything in the D block is considered to be a transition metal. That's where a lot of the typical metals that we think about, iron and nickel and gold and silver, those are located in the transition metals. There's a lot of different properties that you'll see because they can behave very differently because they can lose varying amounts of electrons and not just their valence electrons. So they act a little bit, weird. They are really good conductors of electricity. And they form oxides quite easily. That's where they bond with oxygen. The metalloids, those are the ones that are on that zigzag staircase that separate the metals and the non-metals. They're semiconductors. They can conduct heat and electricity, but they're not very good at doing so, kind of like the metals, or the metals are really good at doing that. Non-metals can't conduct heat or electricity. A lot of the ones, let me just draw a little thing here. These ones down here, will tend to act more like a metal because they're on the metal side of the staircase, whereas these ones up here tend to act more like non-metals because they're on the non-metal side of the zigzag. They can form different kinds of bonds depending on what they're interacting with and what conditions they're under. But we'll talk more about those when we get into those kinds of bonding units. Then we have the halogens. The halogens are over here in group 17. And our halogens, they have 7 valence electrons. And remember, everything is trying to get up to 8 valence electrons in order to become stable. These are non-metals, so they're going to gain electrons. And to get up to 8, they're going to gain 1 electron, so that's why they form a -1 charge. All of these ones are going to end their electron configuration with a P5. Okay. Now, the halogens, because they have 7 valence electrons, and our alkali metals over here have just 1 valence electrons, they form salts quite easily because these alkali metals are going to lose their 1 electron to the halogen, and the alkali metal is going to bond to the halogen in those cases. They form very strong acids, which we'll talk about when we get to the acids and base unit sometime later in the spring. And the reactivity for the halogens, it's going to increase as you go, whoops, wrong direction, as you go up the group. So this one is the most active non-metal, fluorine, most active non-metal. The francium down here is the most active metal. Okay. Oh, and this video down here links to a little reactivity video about the halogens. So you can check that out as well. Then we have our noble gases. The noble gases are over here on the right-hand side, the rightmost column on the periodic table. As we know, the noble gases don't react. You guys should remember that from middle school. The reason they don't react is because they have a stable electron configuration. Inert means noble gases. Now, really, the larger ones like xenon, krypton a little bit, they can react under certain circumstances, but we don't talk about that in this class. The AP teacher will talk about that when you get into that, if you choose to take it. Helium has a different number of valence electrons, but all of the other ones down here have 8 valence electrons. And because they are already stable and they don't form ions, we're going to have a 0 charge for those. All of these except for helium have an ending electron configuration of P6. Now, of course, helium, because it only has 2 valence electrons, it has an ending electron configuration of S2 because it's in the first energy level. But those are your groups and families. We have a little video here about the noble gases. It's kind of entertaining with the balloons and everything that he talks about. So click that if you want to watch a little video about the noble gases. But I want you guys to practice with your groups and families and the history of the periodic table in your packet. And just let me know if you guys have any questions about any of this stuff, okay?